For Lab 3, I created and ran a VPython simulation to analyze recordings of a theoretical star's position over time as it orbited a black hole to determine the mass of the black hole. Newton's second law states that by observing the motion of a system, the net force acting on it can be calculated. In fact, the derivative change in the system's momentum over the change in time is equivalent to the net force acting on the system. So in the case of the simulated star and the black hole, where it is assumed that the only force acting on the star is the gravitational force of the black hole, then the net force can be computed using the equation for Newton's law of the universal gravitation. It is important to note that the change in momentum of the star is the effect of the change in the net force acting on the system. Although the values are equivalent, they are distinct concepts. By iterating through the star's position values, the change in velocity and therefore the change in momentum of the star over that period can be determined. The corresponding derivative, the change in momentum over the change in time, follows. Newton's second law states that the net force must be equal to dp dt. The parallel component of the change in momentum is the change in the magnitude of the momentum, and the corresponding perpendicular component is computed as the difference between the total change in momentum and the computed parallel component. Finally, the mass of the black hole is determined by the gravitation force equation using the star's mass, the net force, the distance between the star and the black hole, squared, and the gravitational constant. When the simulation runs, it can be seen that as the star approaches the black hole, both components of the change in momentum increase, with the parallel component pointing forwards along the star's motion since the velocity of the star increases. As the star passes the black hole, the parallel component decreases, and at the moment when the star passes, it flips to point opposite the direction of the motion. Now the velocity of the star is decreasing as it heads away from the black hole. Although the magnitude of the net force on the star increases as the star goes through the perihelion portion of its orbit and decreases through the aphelion, the direction of the net force always acts towards the black hole. My computed mass at each time step varied, but the average mass was around 1.9888 times 10 to the 31st kilograms, but the minimum and maximum varied by 3.74 times 10 to the 28th kilograms, which is a large value, but it's still several orders of magnitude below the actual mass. The only thing that can be inferred from the position data of the star, assuming that the black hole is placed at the origin, is the black hole's mass. Nothing can be said about any other properties, such as the size of the black hole. If this black hole was replaced by a new black hole and the star's observed motion remained the same, it would appear identical and we would conclude it had the same mass.